Imagine a world where the same rules that dictate the swirling motion of galaxies also guide the intricate dance of subatomic particles. Every moment of existence, every interaction, every phenomenon, from the gentle glow of sunlight to the cataclysmic explosion of a supernova, is governed by these invisible threads, fundamental principles that weave the fabric of reality itself. These rules, encapsulated in the standard model of particle physics, are humanity's attempt to decode the universe's most profound mysteries. At its heart lies the realization that all matter, energy, and forces are interconnected by fundamental particles and interactions. The standard model identifies 12 elementary particles that form the building blocks of the universe. These include 6 quarks, like the up and down quarks that form protons and neutrons, and 6 leptons, including the familiar electron and its elusive cousin, the neutrino. 4 fundamental forces, electromagnetism, the strong nuclear force, the weak nuclear force, and gravity, govern the interactions of these particles. The standard model explains 3 of them through force carrier particles like photons for electromagnetic force and gluons for the strong force. Discovered in 2012, the Higgs boson is the linchpin of the standard model, explaining why particles have mass. Without the Higgs field, particles would zip through the universe at the speed of light, and the formation of matter as we know it would be impossible. But even with its elegance and accuracy, the standard model is incomplete. It cannot explain dark matter and dark energy, the mysterious entities that make up 95% of the universe's total mass energy content. Despite its universal influence, gravity is absent from the standard model. And why does the universe exist as mostly matter, despite the theory predicting equal amounts of matter and antimatter? Imagine how mind-boggling this interconnected web is. Everything you see, feel, and experience is a product of these rules. And yet there is so much we don't know. Hidden dimensions, undiscovered particles, and forces that may lie beyond our current understanding. Imagine holding a manual that explains everything. The invisible rules guiding the universe, from the birth of stars to the formation of atoms in your body. First proposed in the mid-20th century, the standard model of particle physics is that instruction manual. It doesn't just describe reality, it deciphers the cosmic blueprint. Within its pages are 17 fundamental particles, each playing a specific role in the universe's grand play. The electron, a household name responsible for electricity, magnetism, and chemical bonds. The enigmatic quarks, which form protons and neutrons, the building blocks of matter. The photon, a particle of light, enabling us to see the world and feel the sun's warmth. But there's one particle that remained a ghost for decades, the Higgs boson, nicknamed the God particle. Picture this. Deep underground near Geneva, Switzerland, lies the Large Hadron Collider, a 27-kilometer-long ring designed to smash particles together at nearly the speed of light. In July 2012, after decades of searching, the LHC provided humanity with a moment of profound triumph. The discovery of the Higgs boson was not just an experiment success, it was the confirmation of a theory predicted nearly 50 years earlier. The God particle was no longer a myth. Its detection explained a fundamental mystery of nature, how particles like protons, neutrons, and electrons acquire mass. Without the Higgs boson, the universe would be weightless, a barren void of massless particles speeding endlessly through the cosmos. The Higgs boson wasn't the only mystery solved. The standard model also predicted and later confirmed other exotic particles. Gluons, the glue holding atomic nuclei together. Imagine the power behind nuclear fusion in stars, driven by gluons. Neutrinos, ghostly particles that pass through you by the trillions every second, yet remain almost undetectable. How do they fit into the cosmic puzzle? These discoveries turned particle physics into a treasure map, leading scientists to unlock the mysteries of existence. But the standard model leaves tantalizing questions unanswered. For example, dark matter, the invisible substance that shapes galaxies, could it be linked to undiscovered particles beyond the standard model? Extra dimensions, Could hidden dimensions explain why gravity is so weak compared to other forces? And the matter-antimatter imbalance, the universe should have been destroyed at its birth. Why didn't it? The Higgs boson discovery was just the beginning. Each answered question reveals new mysteries, new frontiers waiting to be explored. What else lies within nature's instruction manual? And how much of it have we yet to decode? The intrigue deepens as every experiment, from the Large Hadron Collider to neutrino observatories deep underground, brings us closer to understanding the ultimate rules of reality. The standard model of particle physics, first proposed in the mid-20th century, is often described as nature's most fundamental instruction manual. Imagine it as a detailed guide that explains how every visible and invisible part of the universe works, from the smallest particles that make up matter to the forces that govern their interactions. Yet, the standard model isn't perfect. It doesn't explain dark matter, the mysterious substance making up 27% of the universe. It doesn't include gravity, the force that binds galaxies together. And then there's neutrinos. Once thought to be massless, these ghost-like particles challenge the standard model with their tiny, measurable masses. What lies beyond the standard model? Are there unknown particles or forces waiting to be discovered? Could a deeper, more unified theory, like string theory, hold the answers? Each experiment, every collision at the Large Hadron Collider, brings us closer to unraveling these mysteries. But one question remains: how much do we really know about the universe? The standard model is a triumph of science, but it's just the beginning. The deeper we look, the more questions arise. Will we ever find the ultimate theory of everything? Or will the universe forever keep its secrets? Subscribe and join us as we uncover the wonders of the universe, one particle at a time.